Hi all, welcome to another episode of Theoretically Podcasting. This is Vasu Sham, and in today's solo episode, I will discuss the application of renormalization group methods to deriving the generalized central limit theorem. So it's a somewhat unconventional extension of the RG logic, but it's interesting to see that it plays out perfectly well. What I will do also is follow two separate references that derive the same result. And the result, just to make it clear, will be the form of the characteristic function of the Levy distribution, which takes over from the limiting Gaussian distribution for the sum of an infinite number of independent, identically distributed random variables drawn from some distribution at random. So what we'll see is that in these two references, the logic behind the renormalization group will be slightly different. So the version of the renormalization group logic followed in one will involve this notion that it's about putting a fiducial cut in our system, such as the one between low and high energy modes, and saying that physical observables are insensitive towards this cut. The second notion will be the more conventional blocking and rescaling type version of renormalization that, say, Kadanoff was known to have made sense of. So it's this sort of Kadanoff-Wilson version of the renormalization group. Before proceeding any further, if you like this kind of content, please consider subscribing to the channel. It would greatly help. And if you like this video in particular, please leave a like and share. So the references I'll follow are these two. So the first is titled, these are notes called the Generalized Central Limit Theorem and Extreme Value Statistics by Ariel Amir. And the second is the following paper that I got from MathPH, written in 2010 by these authors, titled The Generalized Central Limit Theorem and the Renormalization Group. So this paper follows the block spin type approach to renormalization, whereas this one is a little bit more abstract and uses this, well, it introduces a kind of cutoff that can be moved, so to speak. Well, not even more than a cutoff, it's really a sort of floating RG scale that can be moved, and no observable will be affected. So before going into the generalized central limit theorem, let's just recall the very basic notion of the original central limit theorem, which states that if we have some distribution from which we're drawing n random variables, and this distribution has a finite mean and standard deviation, then the sum of these random variables shifted by the mean and divided by this factor of the standard deviation times the square root of the number of terms will approach a Gaussian random variable with drawn from a distribution with mean 0 and standard deviation 1 as the number n goes to infinity. Right, so that's the regular central limit theorem. Now, if P does not have a finite variance or mean, then there's a generalization of the CLT, which will lead to a different form of scaling that depends on the power law tail of the distribution. This is very important. Basically, as a result of these power law tails, we'll see that actually the sum of n variables will be dominated by rare events. So that's kind of the punchline. This is why the subject is referred to as extreme value statistics. Okay. So the basic idea here, and also in the other reference, will be that the probability distribution for a sum of two random variables is going to be a random variable drawn from a probability distribution given by a convolution of the original probability distribution. So in fewer words, if x and y are random variables drawn from distributions f of x and g of y, then their sum z, x plus y, is drawn from the distribution given by the convolution of f and g. As a consequence, the characteristic function, which is the Fourier transform of the probability distribution of the probability density, for the sum variable is going to be the product of the characteristic functions of the original f and g. And this goes on if we are taking sums not just of two terms, but say of n terms. And then what we're going to have is a characteristic function that's going to be a product of n individual probability distributions. And a major theme in this reference is that of the Tauberian theorems that relate the small omega or small frequency behavior to the large x behavior. So the tail behavior of the probability density, that is a large x behavior of p of x, will be given by the small omega behavior of the characteristic function. So very quickly to see the utility of this in the case of the standard central limit theorem, let's take the case where we're considering the sum of n little n random variables drawn from probability distribution given by probability density p of x. The characteristic function g sub n for the sum will be the nth power of the characteristic function f. The characteristic function f is the Fourier transform of p. Okay. Now, we can expand near the origin both the kernel of the Fourier Fourier transformation and f. And here they're missing an x, but that would be the expansion. And here a and b are related to the first and second moments of the distribution. Again, characteristic function has a very similar role to the moment generating function. There's just more i's involved. Okay, so first, a is related to I times the mean, which is 0 in our case. B is related to the standard deviation. Perfect. So g is going to be f to the power n, and in this small omega approximation is going to be 1 minus sigma squared omega squared over 2 to the power n. Now the omega squared came from this expansion. Okay. We raise this factor into the exponent with a logarithm and then expand the logarithm for small values of omega squared. And what we find is e to the power minus n times sigma squared omega squared divided by 2, whose Fourier transform or inverse Fourier transform gives us Pn, which is Gaussian, standard central limit theorem. So you see, they comment on the fact that the tail of p of x was essential for establishing the behavior of f for small frequencies. And what we'll see in the generalized central limit theorem is that the power law tails lead to, well, I mean, or in other words, what we can derive will be the form of the characteristic function from which, well, we can infer the property of the tails, and we'll see that they're going to be power law tails. Okay. Here they comment on a case where we can explicitly see that this central limit argument fails. That is when we have a Cauchy distribution. So the probability distribution for the Cauchy distribution has the following form. Its Fourier transform is very simple. And if we had a sum of n random variables drawn from the Cauchy distribution, then the characteristic function associated to that sum will just be the following function where n is in the exponent, because we're taking the product of these. Okay. It's easy enough to do the inverse Fourier transform, and we discover that, well, we don't get a Gaussian distribution, even when n is very large. Instead, we get the following Cauchy distribution. It's yet another Cauchy distribution. So let's diagnose the reason for this failure. And, well, what we'll see is that, in fact, it's related to the moments of the Cauchy distribution not necessarily being finite, the low moments. Okay. So in that case, there's a generalized central limit theorem. And here, what all we'll assume about the distribution, since we don't know its explicit form, is that there's a stability. And the stability of a distribution means that if we add two or more variables drawn from the distribution, then the distribution of the sum will retain the same shape, meaning it'll be identical up to some shift and scaling by some undetermined factors of the original distribution. Okay, so clearly, if the sum of a large number of variables drawn from any distribution converges to a distribution with a well-defined shape, it must be such a stable distribution. All right. And this family of distributions is known as the Levy-stable distributions. So there's going to be a family of distributions involved, as we can already see. So the Gaussian distribution does obey this property. And now we'll discover the form that the family of these distributions will take. Okay. So once again, we set it up by having partial sums S sub n and shifting them by B sub n, dividing by A sub n. And here we'll basically say that B sub n is going to be when the mean is finite, it's going to be proportional to the mean. Else we set B sub n to be 0. And what we want to know is what the limiting form as n goes to infinity of P is. Okay. The characteristic function, when we take y to be c times a, has the following property. We have p tilde y. Oh, sorry. The characteristic function is going to be given by var phi of omega, right? And we see that when we scale c by a, then p tilde has the following form. It's 1 over a times p of y over a. And then the characteristic function is going to be invariant under the scaling of the argument. And this is just a result of a direct calculation involving the Fourier transform formula. But you see that this is, as it should be, the 1 over a prefactor is canceled, since the characteristic function must be 1 when omega is 0. So that's a consistency check. Similarly, when we need to shift by b, what we're going to do is define p hat to be p tilde, that's a p tilde as we have it here, of s minus b. Right, so it's ultimately of p hat that we're going to ask the properties of, so when we take n to infinity. And what we're going to look at is not necessarily for p hat itself, but of its character. We're going to look at its characteristic function. And if var phi was a characteristic function of the probability distribution p tilde, then for p hat, it's going to be e to the I bn omega times var phi, and that's just, again, a consequence of the Fourier transform formula. Now, the RG logic of putting in a fiducial cut and saying that any property of interest, any real quantity should be independent of it, comes in when they say that we're going to take big N to be little n times m, where n and m are two large numbers. So the idea is that you can think of S sub n, the partial sum, in two ways. It's the sum of n of the original variables, or it's the sum of m variables, each of which are themselves the sum of n variables, right? And so big N is n times m, it works out. But you see, given that the characteristic function only depends on big N, and therefore on the product n and m, it should not independently depend on either n or m. So that'll be the key RG-like trick. It's like saying you move the RG scale and physical observables are independent. That's how you derive RG flow equations. Now, here we have the characteristic function when we take, so we say that the sum of n variables drawn from the original distribution, we have the following characteristic function, right? But now we're going to take the sum of m variables drawn from that distribution. Okay, so we're going to have to raise this to the power m. Right? The whole thing is going to be raised to the power m, and that's f. But f, it only really depends on big N. And so it only depends on the product of n and m, not n and m separately. Here's the RG argument. The derivative with respect to little n of f should be 0, right? And this is f. We've just taken this factor into the exponent, put in a log, and then defined m to be big N over little n. Perfect. So then what they do is write down, expand this differential equation, identify a and omega, call it a variable z, and then they implicitly write this in terms of constants times these logarithms of phi. So they basically set this jumble of derivatives of a to c1, one of the constants, and this jumble of derivatives of a and the derivative of c to c2. So they start by solving this differential equation. And we find is that var phi has the following shape. It's e to the power a times mod z to the power c1. All right, where c1 was this, all of this. And that'll matter later. Okay, and so that's the solution to the homogeneous differential equation. Now, guess the solution to the inhomogeneous equation to be of this form. And we find that we basically have a determination of D. And when C1 is not equal to 1, we found a solution. When C1 equals 1, we make a different guess, right? So instead of having just dz, we have dz log z. Okay. Then again, we have a relation between D and C2, right? Okay. Then recall that C1 was itself this function of A. And so log A, or rather A, is proportional to n to the power 1 over C1. Similarly, we can determine C in terms of C2, or C in Cn, little cn in terms of C1 and C2, and we find that, well, little cn is proportional to 1 over C1 minus 2. Rather, the derivative. Then they go into different cases for different ranges of these constants. But let's just look at the case where C1 is not equal to 1. Then var phi is e to the power a mod z to the power C1 plus dz. Right, okay. So if this is the inverse Fourier, or if this is the Fourier transform of a probability distribution, then var phi of minus z equals phi star of z. Right, so you want the probability distribution originally to be real. Therefore, the characteristic function takes the following form. Right, it's e to the power a omega to the power c1, or e to the power a conjugate omega to the power c1 if omega is greater or less than 0. And we can rewrite this in the following way, where the sine of omega times the tan factor is a way of encoding these cases. Now, the asymmetry of the distribution is determined by beta, the constant beta. Okay, so now, again, with the Tauberian theorem, they say you start with a probability distribution that had the following power law form when x is greater than some x star. So this is the tail behavior of the probability distribution. Now, by doing Fourier transform and going to the small omega region, we find that actually, in that case, for small omega, we have that phi goes like this, and therefore var phi goes like 1 minus c omega to the power mu. Note that this is exactly what we'll get by doing the small omega expansion of our little var phi here. Right, so this is saying that when we do the inverse Fourier transform of this characteristic function, the probability distribution we obtain has a power law tail. Therefore, it's one of those heavy-tailed distributions. Now, they go on to analyze the various cases in a lot more detail, and they do very interesting analyses and go into the separate cases. So they rederive the Levy distribution and so on, and even do some numerics. But I just wanted to stop at this point, which is the point where they obtained the form of the characteristic distribution for this entire family of distributions. So the point is that we are dealing in entire families here because we have the constants a and beta. Or rather, we have the constants mu, a, and beta. Now, here I'll jump off to the other reference where they use a slightly different notion of RG, namely the one coming from the block spin transformations, but they essentially arrive at the same result. To see that, what they actually do is they start by considering a discrete random walk. So setting this up as a random walk will just make it much easier. It's a one-dimensional random walk we'll just make it much easier to talk about rescaling transformations. So blocking and rescaling transformations. Okay. So basically, this is the rule for the random walk where n denotes the density of walkers, right? And rho is the symmetric probability density function such that rho u du is a probability of a step taking value and u in the interval u to u plus du. Okay. Great. So here, the RG logic comes in by saying, consider what happens when you take two steps. Okay. When we take two steps, then we're going to have to first use this rule and then use it again. So you use it for one step and then use it again, which means that this convolution rule between rho and n is to be repeated with yet another rho. So you have rho convolution n. So this is the convolution of rho with itself. And here again, we see that we're going back to our rules for the probability distribution over the sums of random variables. So that's coming back. So then the rescaling step is to say that we define a new probability density for the paths n prime of x prime t prime as n of ax prime 2t prime. Okay. And then they define an RG transformation, which is just given by the convolution of rho with itself, but it are multiplied by a and evaluated at the argument ax. So that's the RG transformation. And they talk about how we can make sense of the limit where m goes to infinity, and we apply this RG transformation m times. Okay. Okay, so now let's take this, into consideration. So let's forget about the random walk, right? So we've defined the RG transformation. We have rho, right? That's the distribution of interest. Let's set aside n and just ask about moments of x under the distribution rho, okay? So we find the following equation, which is a very interesting little word identity, relating the nth moment of x under the RG transform distribution being related to product of these lower order moments of x in the original distribution. So it's a sum of products. So when n equals 1, we get the following simple relation. And if we have zero mean, so if we center the distribution, then the RG transformation doesn't do anything to the mean. Now, when we look at the variance, under one RG transformation, this is the rescaling that is incurred by the variance. Now, the question is what happens when we do m such RG transformations and take m to infinity? Okay. So different things can happen based on what the magnitude of a is. So if a is greater than square root of 2, then, well, as m goes to infinity, the variance just goes to 0, meaning that the limiting distribution is a Dirac delta function, the large m limit. So it's some deterministic thing. When a is less than the square root of 2, well, the variance diverges, the Levy case. When a is the square root of 2, here we recover the regular central limit theorem. Okay, so x squared doesn't change under the application of the RG transformation. Then we can ask about the fixed point distribution. So when we're at a fixed point, then t rho equals rho, but tm rho naught also equals rho naught. So then we have our void identity rewritten, but now we're comparing the same kind of kinds of moments. So we can just solve this equation. And its solution is given by Wick's theorem, which means that the distribution we were considering is a Gaussian distribution. Right? So this is Wick's theorem. Notice that the 2n power moment is just the nth power of the second moment with these combinatorial prefactors. Great. Now, we can ask more generally about the RG transformation of the characteristic function. And the result of that transformation is to rescale k by a. Okay, now at the fixed point, we get the following equation for the characteristic function under this RG transformation. Right, so the only non-trivial thing was to identify what the RG transformation was. Once we had it, then understanding the fixed point equation becomes rather simple. And then we can define alpha to be log 2 over log mod a. and find that when A is positive, the solutions to this equation have the following form, which should be very familiar. This is exactly the form of the Levy alpha stable distributions that we saw in the previous reference. The role of mu in the previous reference is played by alpha. The role of omega is played by k. And we had little a there, which is big A here. So this is a slight reshuffling of the notation, but we recover the same result. So both these different perspectives on RG applied to this specific context seem to give the same result. And it's interesting that one seems much more available than the other, namely the former, where we can just take some variables, sort of write it as a product of two other variables and say that, well, the result only depends on the product and therefore not on the individual variables. That seems like a much more available move. But what I'm curious of is whether always in such cases, there's also some kind of physical RG transformation available, where there's a block spin type RG transformation, which yields the same results. I'm curious if you see other applications of such logic in sort of unexpected situations. If you have, please leave references in the comments. I'm sure the other viewers would appreciate them. I hope you found this amusing, or as amusing as I did, and hope to see you again next time here at Theoretically Podcasting. Take care.